Okay, good morning, everybody. Welcome to this CIBSE West Midlands seminar. This has been finally put on by Cetotherm. This is being repeated this evening, so if you have to drop off the call at all, you can watch it again at 6 o'clock this evening. We run a series of seminars throughout the year, generally 2 a month, on technical and vocational topics. If you have any ideas and suggestions for topics, please contact myself in details above or any of the committee members. So today's session is about the HIU, I'll say it. Yes, it's by Cetotherm, and it's been presented by Russell Hillman, my apologies. He's been involved with the heating industry since 1988. He's worked for BSS, Pegler Yorkshire, Mitsubishi Electric, DMS Metering Solutions, and now Cetotherm as external sales manager, HIU and heat stations. And without further ado, I'll let Russell carry on with his presentation. Just a quick one, any questions, please put them in the chat box and we'll cover them at the end of the presentation. Thank you.
Good morning, everybody. I'd like to introduce myself. My name is Russell Hillman. I'm the area sales manager for Cetotherm. Just to kick off, we've got a short introduction video just to give you an overview of the company and the products that we supply. So things like heating, hot water and cooling of buildings is our key product base. This is the video. I hope everybody can hear the sound. Okay, as you've seen there, we're involved with the heating, hot water and cooling of buildings. So the introduction film covers some of the manufactured products that we make in Sweden, France and the Czech Republic. So the parent company Cetotherm is Swedish owned, been around since 1923. We were owned up until 4 years ago by Alfa Laval. Our factory is just opposite the Alfa Laval factory. So again, we have a lot of synergy between Alfa Laval and ourselves. Heat interface units, pressurization units, cylinders, tap water systems and substations for distribution and heating and cooling. Today I'd like to focus on the heating and cooling substation design and some of the aspects of the networks they connect to. Oops. So district heating is important and growing industry, but it's also crucial to enable us to reach a better tomorrow. You take, the crisis we've got at the moment with the rising oil and gas prices, we're all trying to get to a smarter way of working. It will help us all fulfill the growing demand for heating throughout the world, with less environmental impact on individual localized heat sources, giving a brighter future for generations to come. There are many types of heat sources for district heating, but the principles are the same in general design. When it comes to heat transfer, using a substation or heat interface unit, because that's all it is a glorified heat interface unit. In this presentation, we're going to look at proven design principles, which we have helped customers worldwide by producing highly efficient heat interface units and substations. So again, this is our core product. This is what we've been involved with since 1923. District heating is the heating of multiple buildings off one heat source supplied through a network of pipes. As you know, in Birmingham, there's lots of heat networks that's cropping up. District heating offers the promise of smart solutions for the supply of low carbon heat to homes, business and public buildings. There's a growing case being made for expansions of the heating networks. A recent report by the Energy Technologies Institute, the ETI, suggests that using low carbon fuels, they could potentially meet up to almost half the UK demand while reducing the national decarbonisation costs up to £3 billion. The UK now is a net importer of natural gas, and this being a factor has been generated further interest in district heat as means providing greater energy security. You just have to look the last couple of months with the rising energy costs, with gas and oil going up, it has impacted on people's day-to-day and businesses in day-to-day paying of energy costs. If done properly, this approach to heat will also bring carbon reductions, benefits the local economy and reduce fuel bills for the end user, including householders. There are many different ways to supply heat to a network. There are some of the classic forms of heat generation, so geothermal, so taking latent heat from the ground, including mine heat. Mine heat is quite a key one at the moment. We're working with a company up in the Newcastle area where they're looking at recovering mine water. Industrial waste to heat, the manufacturing process. A lot of industries produce heat, residual heat, and it's not utilised and can be used. If you look to Sweden, there's a large timber industry where they prepare wood for furniture and stuff like that. A lot of the waste that's generated from there then will be pumped into district heat networks. Energy from waste, incinerating viable waste product produces heat. Again, there's a lot of energy there. Again, most major cities have a massive amount of waste energy that they could potentially use in district heat networks. Again, fossil fuels. Again, this is the oldest form of heat and there's still fossil fueled power stations in the UK. Combined heat and power, where power is generated by the production of heat and as any residual heat is used within a district heat network. Again, London, there's quite a lot of CHPs that provide additional heat into district heat networks. Biofuels. This is heat produced by burning natural fuels. These are fuels that are made by geological process, for example, natural gas, coal or crude oil. So things like wood chip, log, miscanthus. The heat source offering is constantly changing landscape as we look at more sustainable solutions for heat production. For example, river source heat pumps and hybrid systems made up of combined technologies, which can include solar thermal, heat pumps, CHP, heat recovery, especially heat recovery from things like data centres where a hot lot of heat is generated. Can that heat be utilised into a district heat network? Along with other emerging technologies to the market. One thing is always remember is that the principles in the heat network are the same. A heat source or heat sources in a hybrid system are used to provide heat along a pipework, which is then commonly transferred via plate heat exchangers to the liquid circulating around the district heat network. So the evolution of district heating. So here we have in the evolution of a district heat sources over the last 140 years. Steam was originally used to supply heat to the networks. America was the pioneer in this technology. So if you look at large cities, New York, Chicago, Boston, a lot of them run off district heat network provided by steam. In larger cities like New York, this was followed by countries like Russia. A lot of Russian cities still run off district heat network of steam. Over the years, the heat sources changed and combined to give a more efficiency, greener solutions and the provisions for heat to the network. If we look closely at the evolution of the heat networks, you can see the integration of technology and reduction in circulation of the temperatures. So if you look at the temperatures, originally you're looking at 100, 140 plus, real high temperatures. And over the years, the temperatures are slowly dropping, but the energy efficiency is growing. The integration of insulated pipes, especially plastic and polymer pipes. Then you've got the integration of waste to energy plants, geothermal, wind turbines, CHP of biomass, industry waste, heat pumps, solar, CHP. So everything could be added into the district heat network to try and make the system as efficient and low temperature as possible. So district heating, 5 generations. So the first, second, third, fourth and fifth generations. As you can see, the temperature have decreased over the last 130 years to what we recognise now as 4th generation. 5th generation is now standard we should be trying to achieve with the integration of renewable technology, increased control and live data collection as sustainable as possible. The more information you can gather from a district heat network can make the system more efficient by looking at variations in the outside temperature, the inside temperatures, what the buildings are working at, what's the flow and return temperatures. So if you go back to the 1st generation, you're looking at steam about 200 degrees and return of 80. Up until now, the 5th generation, where you're looking at very, very low flows and the exchange of heat and cooling excess. 5 to 25 heating and cooling, integration of heat pumps to obtain 55 degrees. From 2017, that's what we'll be looking at, is to try and achieve the lowest flow as possible, to try and make the system as efficient as possible. Building connections. Did someone say about the slides changing?
Yeah, they did. Mine are changing, but if anybody else could put a hand up if they have an issue. I think I was just going to suggest that a mic logs off and put. Yeah, I think it might be easier to log off mic and come back in again, Mike Man.
Slide 8 is up at the moment, yes.
Yeah, I think he needs to log off mic and come back in again. Well, we'll answer questions at the end. Let's just pick that question up now, Mike, by Russell from Steve.
What did he say?
At 50 degrees C primary flow, how do we ensure domestic hot water temperature?
Right. So what tends to happen in Nordic countries is they have a 3-pipe or 5-pipe system. So heating is done via one set of pipes and hot water is done via another. So the hot water flows at a slightly higher temperature to provide you with decent hot water. We do come across this quite often in the UK where people are using heat pumps where the flow is, 51, 52. How do you generate hot water? So that's something you've got to bear in mind when you're looking at hot water generation. Is that okay?
Steve, do you want to put a thumbs up for the answer to the question?
We can cap that off. Okay.
Yeah, I can't see a thumb, but let's carry on, Russell, and we'll up here.
Okay, that's fine. That's fine. I'll make a little note of hot water. There are also many different options for building connections to a district heat and location of the substation or heat interface units. This all depends on who will own and maintain the substation or the heat interface unit. It could be the building owner, the energy company, or the end user, but no matter what, the energy efficiency is always the key. Today, we're going to focus on substations, whether it's connected and located at the building with a single connection or the heat source feeding multiple buildings. Some of the key criteria must be considered, and the same core principles for the design needs to be careful considering the high energy efficiency and they give us all a greater solution. So when it comes to building connections, if you look at the Nordic way, it tends to be the heat interface units are owned by the utility company, and they provide the billing for the heat and hot water that's generated. So it's a slightly different way than the UK, where the building owner or the estate owner owns it. It's generally done through the utility company. They class it as a fairer way of doing it, and then they get full technical backup and support when it comes to breakdowns. So key criteria for high energy efficiency. By looking at the world's biggest heat networks, we can learn some very valuable lessons. Small changes can increase the efficiency and maximize the use of energy. The key to high energy efficient heating systems is the lower primary return temperature and a high primary delta T. The more efficient systems itself becomes. So what you're looking at is low primary return temperature, high delta T. So you're extracting as much energy as possible out of the flow that goes into that building. Key influence for high energy efficiency. A key influence on the primary return temperature is the secondary side return temperature. This is better we make the delta T on the secondary side, the better the primary becomes. By controlling the secondary side pumps through the substation as a package, the pumps become pivotal part of in aid of maintaining the return temperatures on the primary and secondary side. So again, low secondary return temperatures, high secondary delta T. So why low return temperatures? So again, yourselves, you're going to be designing the heating system for that building. So why should we try to achieve the lowest return temperature as possible? Not only does this increase the efficiency, but also reduces the cost. By reducing the flow, we can reduce the pipe size, giving a reduction in the cost of the pipes, the pumps, the valves, and other components, which turns to reduce electricity cost and circulation of pumps. So if you're going for smaller pumps, again, you're saving energy in the long run. With a mass flow at the lower temperature, there is less heat losses in the distribution network. Again, smaller pipe work, good insulation, cheaper insulation because you're insulating smaller pipes. We must remember the distribution systems are running constantly. Another benefit for reduced return temperature is you can add new connections without replacing or increasing the pipe size. So the savings in distribution system means continuous savings for the energy and cost at all times. So if you look at the slide in front of us, so reduced pipe sizing, capex saving. Again, that benefits you when you're designing a building. Reduced investment cost, again, capex saving. You're looking at smaller pumps, smaller controls, cheaper insulation. Reduce electricity because you're going for smaller pumps, smaller control valves, OPEX saving. So I have conversations with housing associations on a regular basis, and it's not so much the capex saving they're looking at, it's the 25 years of operational cost that potentially saves them a lot of money. Reduces heat loss, again, because you've got smaller pipework, better insulation. Again, it's an operational saving. So over the lifetime of the building, the energy cost is significantly lower. So here we are. We have two examples that demonstrate how changes can affect the whole system in a positive way. They both have the same capacities of 10 megawatts. Case one has a primary flow of 75 degrees, return of 55 degrees. This gives a delta T of 20 degrees with a mass flow of 124 litres a second. The pipe size required this are DN 300 with a pipe size of 2 times 25 kilowatts. So case one. So case two. Case two has the same primary flow of 75 degrees, but the return has been reduced to 35 degrees. Now you've got a delta T of 40 degrees, dropping the mass flow to 60 litres a second. By lowering the return temperature and using more of the heat in the flow, we can reduce the pipe size to DN 150 and reduce the size of the pumps required to 2 times 15 kilowatts. By making small changes how we designed the system in the first place, using more of the available heat, we're able to make considerable savings, not only in the installation fabric, but also of the running costs. So your customer, over the period of the building, can actually save himself quite a lot of money. So DN300 to DN150, you're the design engineers, you know exactly how much difference in price. You know, you're talking a hell of a change when you're looking at changing pipes and valves from 300 mil down to 150 mil. Smaller pumps, smaller controls, so it's a considerable saving. Cheaper insurance, it's cheaper insulation. So increased efficiency in heat production, cutting heat losses from the pipes. So it depends if you bury them or suspend them through the city, as they do in Berlin. Again, it's a better way of doing things, as in smaller pipework. So 6 actions to attain lower return temperature. There are 5 important things to keep in mind when you're trying to obtain low return temperatures. The correct sizing of the substation design, giving the best efficiency. Give him a control of the domestic hot water circuit and maximising efficiency. And again, that's key, as the question was asked earlier on about hot water when you got to a low flow temperature. Using a 2-step connection enables the use of recirculating residual heat in the building to preheat the domestic water on the heat exchangers, making the substation more efficiency. So any waste heat in the building that's not used on heating could potentially be used to preheat the cold water coming in for domestic hot water. This is quite common in Europe, and we see it on a regular basis with some of the hot water stations that we provide. By using the intelligent control, there is more flexibility through monitoring. This enables management of the substation and adjustments without affecting the comfort levels, increase efficiency. So again, if you look at the way it's controlled properly, if you use some smart controllers, if you look at maybe outside temperatures, inside temperatures, knocking down the flow a couple of degrees, but still giving comfortable heat within the building, there's ways of doing things. The use of high quality components within the substation not only helps with obtaining low return temperatures, but also improve the reliability and giving higher levels of efficiency. By having controls at the secondary circuit pumps, we can maximise the reduction in the secondary return temperatures, in which turn will influence the primary return temperature. By reducing return temperatures, not only will you benefit from savings on the long-term costs, you will also increase the efficiency and reliability of the substation. So again, that substation is not working flat out, it's working at a nice comfortable level. So here we have some concrete evidence. So district heating return temperatures, yearly savings. So decreasing by 1 degree. So the district energy company is Helen Limited. They're in Helsinki. Again, we've got a lot of experience because, as I said, most of our market is the Nordic countries. A great example of these principles is the scheme, the district energy company Helen Limited. In Helsinki, with a population of 650,000, 90% of the buildings are connected to the district heating. 90% of the heat is produced by CHP, and the efficiency is more than 90%. So it's rather a big district energy company, and they've almost 900 miles of pipeline with a yearly sold energy approximately 6.7 thousand gigawatts and cooling of 200 gigawatts. Again, there's a lot of businesses that require cooling because of data centers, and data centers are growing. This example, we use Celsius because it's easier to remember. The decrease of 1 degree on the return temperature, they have created a yearly saving of €1 million. And that's just 1 degree. In Helsinki, they encouraged for increased delta T and efficient systems by adding price support to the energy on top of added savings detailed in the example. So they're quite keen on getting everybody on board, and by using smart controls and monitoring the system from the beginning to the end, there's a way of reducing the district heat temperature return and making the buildings more efficient and the heat network more efficient. So what should be included into a substation? When we are designing a substation, it is important to consider all the components that are used carefully to minimize the overuse of valves and unnecessary components. Correct size heat exchangers, control valves and pumps and the combined design selection are very important to the efficiency and control of a substation, along with the temperatures and the flow sensors. When this is all connected through an intelligent controller, you will achieve the ability to monitor how the substation is working, to enable you to make adjustments to its flow through the control valves and pumps, which in turn makes the system more efficient and the saving amount of energy being used whilst not impacting on the end user. So again, above is a simple substation, linked with a smart controller, 2 plate heat exchangers, a couple of temperature sensors and valves, providing heating and hot water into a typical building. Now, 2-step connected substations. So this is what we would provide generally as standard. As mentioned in the previous slide, there's also another step option to design, again, increase the use of energy efficiency and raise the comfort levels. Using a 2-step connection takes latent heat and preheats the domestic hot water. So again, in the summer, your water's coming in at a specific temperature, but in the winter, if you get a really cold winter, that water's coming in a lot colder. So your system's working a lot harder to heat the domestic hot water up to a decent level. Using a 2-step connecting takes latent heat and preheats the domestic hot water heat exchanger. Not only does this decrease the time to heat the hot water initially, it also aids in reducing the primary return temperatures. So it acts as a heat dump to a certain extent. So when it returns back into the district heat network, it's a lower flow again. So again, you're extracting the maximum amount of heat out of the flow that's coming into the building. So making it more energy efficient. There's no waste energy. So what should be included into a substation? So even when we look at the most simple substation designs, like this heat-only illustration, the selection of components can assure that the most efficient solution has been found. This will also create a really reliable unit. It also gives the client is ongoing to manage the substation to full control with integral controls linked through BMS or the addition of smart controller. So there's nothing complicated there. Everything's been selected to work properly within the design of the building. So you tell us the design of the building, the capacity required, and then we can size up the heat exchangers, the valves, the controller. And with everybody moving now to apps or online, rather than connected to a BMS system, there is ways of connecting buildings up or heat stations up to a network so that the system can be monitored. And then you can put into things like weather compensation, you can put into flow and return temperatures, you may get warmer days, colder days. You can look at the orientation of the building, does one building side of the building colder than the other, north facing building where it doesn't get a lot of sunlight. So a lot of that can be taken into consideration when you're what the best valves for HIU control. It depends on the system. It depends on the size of the pipework. It depends on the flow. It depends on the return temperatures you want. We will put differential pressure controls into our heat stations, but onto our HIUs, generally we don't put them on there because it should be done in the pipework. Again, using a pipe sizing tool like HiSopt or something like that, there's plenty of pipe sizing tools out there. You can actually size the pipework up according to what you want. Hopefully that has answered your question on the valves or the differential pressure control. So, intelligent connected controller. The correct design of a substation is very important, but equally good controls play a very large part in creating a highly efficient substation. I'm sure I read somewhere that the intelligent person, or a more intelligent person than me, the whole is greater than the sum of parts. So again, it's making sure that whatever's been selected will work together. By implementing greater controls, we make the whole substation better. By including controls, the substations become a plug-and-play solution, and we're a big advocate of plug-and-play. If the system's been designed properly in the first place, it's a case of delivered to site, plumbed in, connected, and it works first time, other than commissioning. The manufacturer of the substation can support the customer's and contracted engineer, reducing the requirements for specialist and controls. Again, if it's all built into the control panel, it's a case of just quickly connecting to the BMS system, and off you go. Highly efficient substations are usually correctly placed sensors connected to the controls, which enable quick and clear monitoring. So looking at the flow and return temperatures, looking at the differential pressure control. So is there blockages at the filter? Is there blockages at the plate? Has a pump gone down? Is the pump working properly? Is the inverters on a pump working properly? Are they on a fixed speed or on the variable speed? So again, all this needs to be taken into consideration when you're designing a control panel, so everything works together and gives the information back to the end user or the building controller to make sure that they understand. By using low voltage actuators, there's decreased risk to engineers working on the substation, along with less energy used. With Intelligent Controller, it gives energy company, building management and building owners the ability to view, and with the correct given access, adjust the substation without having to attend site. So again, it makes it easier then for if you get a warmer day in the winter, or you get a couple of warmer days or colder days, you can actually change the heat flow and return just by tweaking it via the BMS panel. This also enables substation to be viewed or analysed and diagnosed prior to a site visit from an engineer, reducing the time spent on site and the disruption. So if you know exactly roughly what's going wrong, it gives you a better idea rather than have to turn the whole system off. You know, it could be a blockage on the heat exchanger, it could be a pump that's down, it could be a control valve or an actuator that's not working. But it gives your the site engineer the tools to straight away to pinpoint where the system could be wrong and turn the system on quite quickly and get it up and running within an hour or two, rather than the system being down all day. LoRa ZigBee. So we're looking at, we use a Siemens controller on our whatever you want. Basically, you tell us what you see or what you want, and we can generate. Because we use Siemens, a lot of the Siemens now are working to an optimized system. So you basically is a SIM card plugged into it, and it's connected remotely to the cloud, and you can download the information. So again, it's having that conversation with the building designers, the building users, to find out how they want to run the heat station. Being able to gain remote access can also reduce the need for the engineer to attend site, as I said earlier on. With connected intelligent controls, ZigBee, LoRa, my background's meeting, so LoRa for me was a growing potential. And if you can see the range that LoRa will work at, if you can connect everything within a building to a LoRa system, it makes it a hell of a lot easier for the building landlord or building manager to understand where things are going wrong, because he's getting that information quite quickly rather than chasing through wires. The connected intelligent controls, remote upgrades and updates can be made to software given prolonged life. So again, if you're getting updates from on a BMS panel or to control panel, then you can send that down a wire down to the control panel. Again, you're prolonging that life. All this added together gives energy savings. So again, it's been able to manage what's going around the building by some simple changes. Why a smart connected controller? You ask what the benefits of a smart connected controller. So again, everybody's got a mobile phone, you know what's going on. People now have got their heating connected to their phone, so they can turn on when they arrive home. You know, the people who are lucky enough to have a electric car, a Tesla or whatever, knows that you can set the controller on your phone and you get up in the morning and your car's lovely and warm, ready to go, and the window's defrosted. Benefits of having a smart controller. By monitoring the substation and having remote access, you can implement changes quicker in real time. Monitoring also gives the ability to react to sudden changes in the system, which impact efficiency and the comfort or the overheating or underheating of the building, so you can tweak things quite quickly. By making small changes remotely, the substation efficiency can be increased by increasing the cooling and improving the delta T without multiple visits to site. So you haven't got an engineer tweaking differential pressure control valves or commissioning sets. You know, we can then automatically via whichever system you've got set up. Because the changes occur are small and can be implemented anytime, minimise the impact for occupants given the increased building. So if you look at a government building, if you go past, I live in South Wales, you go past the DVLA, the lights are on 24 hours a day and no doubt the heating's going on. But if you use the building controller and you know at 9 o'clock that everybody's gone home, you could turn the system down a couple of degrees. That makes the system more efficient. So you just imagine in central Birmingham business district, how many buildings are running 24 hours a day, 7 days a week with the heating turned on. Whereas if you was the building controller, you could actually turn it down via your heat station. Smart connected controllers can be configured to raise alarms of changes to the substations, giving improved safety. Again, you know, it could be temperatures dropping inside, outside, flow and return. There could be lots of stuff set up. Have remote access can also give improved service offering to the stakeholders, saving time and money and energy whilst minimising the impact of their clients. So again, you know, if the heating went off in a commercial building, how quick would people notice that the heating had dropped down? In the summer, they wouldn't notice at all. In the winter, they would possibly notice. But again, it'd only be maybe an hour or two. But straight away, you could have somebody, if they're monitoring the heat substation via the controller, they know straight away that there's an alarm being sent, right, his system's gone down or the system's not performing. So straight away, someone's on the case. Also, the ability to monitor and adjust the substation remotely with warnings and changes mean preventative works can be carried out at a regular maintenance and service intervals. Again, you could notice things changing, pumps not working as efficiently as possible, valves not opening as quickly as possible. Again, that's a good way then of going in and just checking the system to make sure it's okay. You know that, you know, maybe there's a bit of dirt in the system, maybe a filter needs changing, maybe somebody closed the valve slightly. By knowing that, you're reacting straight away rather than having to get a shutdown. The changes that are made in real time can also help reduce the kilowatt hours used, meaning the savings start as soon as they applied remotely without having to attend site. So again, it's understanding what the building is working at via your smart and connected controller. These changes also have an impact on other aspects of the substation, giving reduced usage of electricity to the pumps and the controllers. Again, you know, with inverters, you know, the pump's not working as hard as possible and they're just ticking over, just providing the heat that's required. The control valves are not opening fully. They may be opening, you know, a small percentage just to allow a certain amount of heat through. All these actions will help give savings, which will be increased at peak times and making the whole substation more efficient. So again, that system's being monitored 24 hours a day and it's only tweaking open, tweaking closed. If the heat is required, if the heat's not, it's shutting down. If you don't measure and monitor, you won't know the changes are needed to make the system perform better. So again, it's understanding what is going on 24 hours a day, 365 days a year. By using a smart controller on a heat station, you get a better idea then of how the building's performing. You know, you design brand new buildings, you know, and you can design it within an engineer's life, but you can't control what goes on in the building, you know, once you've handed over to your client and the client runs the building. And you'd be quite quick to say that this building's not working efficiently, but with a smart controlled heat station, potentially that could outperform what was expected. And the most important thing is avoiding overheating, and the more control you'll have. So low return temperature is all about the money, and it is all about the money. The capital cost is expensive, yes, we understand. If you look at, you know, over 10 years period, the operational cost is massive. More than 90% of the heating costs of a 50 block of apartment buildings over 10 years are the energy costs, which means that the purchase cost of the smart substation and the installation costs are peanuts compared to the energy costs of more than 15%. By decreasing the temperature of the primary turn, and the heat losses are reduced to a minimum, and the heating system is optimized to its maximum, so it's working as efficient as possible. So you just, in a car, go popping along the motorway at 56 miles an hour. I know it's not always the best way to do it, but it's as efficient as possible. You'll get the best out of the district heating and condensating boiler heat source, but only if you come back at low return. So again, you're all well known in condensate boilers, but again, the condensate boilers want that low return temperature to work properly. On top of the sites connected to a green energy source like solar, heat pumps, heat recovery will optimise the use of green energy, reducing the use of fossil fuels. And again, it's all about an integrated building. You know, we've just said COVID, you know, mechanical ventilation. You know, can you do anything with the waste heat? Can the waste heat be dumped into a thermal store and actually used to preheat the building? There's lots of stuff that could be done. So smart district heat substations, low primary return temperatures, intelligent remote control, district heat in a smart way. So district heat is an important and growing industry. It's also crucial to enable us to reach a better tomorrow. So again, everything's new as beautiful. Can you achieve weather compensation? Yes, if the system is monitored with a heat network, with a heat station, or even with a large boiler system. It's about monitoring and understanding what's going through, where your hot water is being used. You know, can it be reduced down to a slightly lower temperature? Again, taking in consideration Legionella and stuff like that. With your heating, you know, can you be doing? Can you lower your temperatures even in the winter? You know, it's not particularly cold today. You know, do you need to be flowing at 70? No. Can you get away with 60? Possibly. Can you get away with 55? And if you look at heat pumps, you know, they're looking at flowing at 51, 52 degrees. But again, you've got to take into consideration, especially in a commercial building where there's hot water required, is how can you manage everything at all? It will help us to fulfill the growing demand for heating throughout the world, with less environmental impact on individual localized heating sources, giving a brighter future for generations to come. There are many types of heat sources for district heat, but the principles are the same in general design. When it comes to heat transfer, using a substation or heat interface unit. And again, apartment blocks, you'll have the substation downstairs in the cellar or on the roof, and then you'll have independent HIUs in buildings. They do slightly different in the Nordic countries, where they generally don't have HIUs in buildings. They have the main substation, and then they sub-meter then going into apartments. But again, that's controlled with differential pressure control. That can you take into consideration heat meters, all feeding back into a central communication system, so they actually know what's going into a building. Better insulation generally in the Nordic countries and in the UK, but again, we're getting there slowly. If this presentation, we're going to look at the proven design. So what we try to do is what we do on a regular basis. Cetatherm have been around since 1923. We've got a lot of district heat stations in London and around the country. We're at the CIBSE Build to Perform in London in November. So if any of you want to come along, have a look at our website. There's lots of information on there. For ourselves, it's things like the heat stations, the HIUs, hot water package plates, which can offer you a substantial easier way of doing things rather than designing the system yourselves. If we can be of assistance, by all means, give us a shout. So hopefully, you've enjoyed my little presentation. I'd like to say if there's any questions, anything I can give you any more attention to. Again, if you want any literature, documents, by all means, drop me an email, and I'm more than happy to share the information with you. Is there any questions?
So there are some questions in the chat box.
Yeah.
We've got one from Gordon Pringle, and it's a statement and then a question at the end.
Yeah.
So many thanks for a good presentation. CIBSE Heat Networks Code of Practice in the UK, brackets CP1.
Yes.
Close brackets. There's numerous best practice recommendations recently with cost-effective adoption. Many of these will, the screen's up then, will ensure greater transparency with water as heat transfer medium of all such systems. Water quality is key. The demands of heat pump net uptake. Heat pump AM17 follows a best practice guidance. Which aspects do you feel is the best on the CP1 now?
For ourselves, it's making sure that is following the guidelines of the CIBSE guide, to make sure that all our product complies with that. And we're keen to make sure that whatever we supply in the UK, it complies to the CIBSE regulations. With district heating for us is not a growing thing. It's our backbone of our business. Like I said, we've been involved with optimized heat stations now in the last couple of years, mainly because we see buildings and technology moving forward so quite quickly by making everything work together. So, design of the heat network, the substation, the HIUs, the control within the building, and even you've gone about the water conditioning and the treatment of the water. Now, we do a lot of work with mine water recovery, and the biggest issue there is iron oxide. So again, is that treatment of the water, if the water's not been treated properly, potentially that could have a knock-on effect, not only to the heat station, but the heat network furring up the pipes. So it's taking into consideration everything that's going on within the heat network. It's not just about, oh, that's the substation. Well, actually, what goes on in that building, what goes on from where the heat comes from, where the heat returns to. So it's understanding everything more than anything.
Okay, thank you for that. And we've got one question there about the presentation. We should have mentioned before that the presentation is being recorded and will be available on the CIBSE headquarters and also the CIBSE West Midlands websites. So you'll be able to have access to it. I understand there's a short delay in getting them posted due to the number of presentations taking place at the moment, but the actual recording will be posted on, as I say, on the CIBSE headquarters website and on the CIBSE West Midlands website.
On our website, we've got some information on there. We've also got a couple of videos where optimized heat stations. So we've done a big one near Malmo, where they've just built, the Swedish government have just built a new town. In the town, there's no cars allowed. Any cars are on there have to be electric. They have to be shared. So anybody, once they use it, can book. It's all about transportation. It's about trying to make the modern village more than anything, and it works. My boss Alan's been there, and he said if you go to the system, he said there's good transport links, there's shops nearby, there's schools nearby, and it's trying to make everything holistic so it works together. And that's all down to providing a decent district heat network, so everybody's got the heating, the hot water, but everything is joined so they can actually control it. So again, warmer days, cold days, they can knock the temperature down, knock the temperature up. Constant hot water at a regular temperature. It's making things simpler. Unfortunately, in the UK, we live in a small island, and we're very, very congested, especially if you go to the more larger cities like Birmingham, Manchester, and London. You can just imagine trying to bury heat network pipes into central Birmingham. That'd be quite fun.
Just a quick observation I made is that when you got a city, when you got such as data centres generating heat in the winter,
yes,
I wonder whether the heat interface units actually have the capability of giving a credit to those businesses generating heat in the winter.
It can do. We do cooling substations as well. So again, because with data centers, the key now to how the UK runs, how the world runs, because as I said, everybody's got a mobile phone, a laptop, or connection. They generate a massive amount of heat in these data centers. Well, normally, what would you do with it? Can you recover the heat? Could that then be integrated into maybe a preheat into the district heat network? So again, there are ways of doing it, and it's that smart design of the system. The waste energy from a data center, could that be plumbed into the accumulator or the buffer vessel of an energy center, so it's preheating the water again? So there's ways of doing it, and it's quite common. As we used to be owned by Alfa Laval's key purpose to chase at the moment is data centers. So there's a lot of heat that's required. You've got to keep these data banks cool. What are you doing with that heat? Well, if you think about it, every city has a data center or multiple data centers. Potentially that could be free energy to a certain extent, but there could be a kickback to the data center for providing that preheated free energy.
We've got one other question. It's from JM. A pattern design town. It's like it sounds in some ways what I'm saying there is pattern design town is like the Milton Keynes of the modern day, isn't it?
Yes. If I remember the town in Sweden, I think it's called Lund, and that's what they've basically done is they've they've sat down with the town planners, they've sat down with the consultants, they've sat down with the builders, and they've sat down with the architects and gone, this is what we want to do. So the buildings are very well integrated, ventilated, very well insulated, low energy technology in the whole, so district heat networks, low energy lighting, controls, and all stuff like that. So you basically had a passive house being designed for a city rather than, or a town, rather than just one or two buildings. And potentially, you know, there is lots of options with building to a passive house design, especially with apartments and domestic properties, because again, COVID, ventilation, right? You build the passive house, yes, there's got to be a certain amount of ventilation, but again, if you're well insulated, you know, you could be saving yourself a lot of money. Now, a couple of years ago, when I was at the a metering company, I went down to Devon and Peyton College, and they built a passive house on site, and this runs off solar thermal, solar PV, and the only heating source they've got in is a couple of little Dimplex panels, and the cost for them to build the house was only £150,000, and they rent it out on a regular basis, so they're constantly being monitored. So that's something potential that is out there, but you just need someone to step up and go, right, okay, we're going to build a village, you know. Okay, it's all well and good having the red raw wimpy stock house, but why don't the building developers build something that's passive house potential?
Certainly with the amount of new building going on at the moment, every place you go past there's a big sprawling estates being built. It seems a missed opportunity that you don't have some sort of a heat network built into these areas. But
it is happening now. One of our biggest customers on our HIUs is Barratt. So in London, Barratt on the apartment blocks generally use HIUs with the heat network. They're actively going out now and looking at, when they're building their low-rise, can we build to a district heat network? Now that could be using heat pumps, that could be using a CHP, that could be used, you know, waste to energy plants. So Barratt are actively looking at the moment. There's a very, very large Swedish construction company, Skanska, who have partnered with the very large blue and yellow shopping company that every town has got one, and there's a company called Bocklock. So Bocklock build prefabricated homes to high-level Swedish standard. They're looking at passive house standard on their apartment blocks at the moment. So they've got a couple of schemes, one down in Bristol and a couple in London, but Bocklock would be worthwhile looking at, because I'm saying they build to Swedish standards.
anything else? Okay, any more? As we haven't got any more questions, I'd like to thank Russell for his very interesting presentation on behalf of the CIBSE West Midlands. I should have mentioned before, I'm actually the papers chair for CIBSE West Midlands. And again, as I stated on the chat, if you have any ideas for future topics, please contact myself. My address, our email is on the chat, or any of the committee members. So thank you for your attendance, and thank you, Russell, and I'll see you later on this evening.
Okay, thank you very much. Okay, thank you all. Cheers. Bye-bye.
Bye-bye.